Sometimes just one of these will be running, sometimes another one will have to kick on, and we'll see kind of the effect that has. Block diagram of the system. We've got the input as a percentage of motor power and the output as wash water flow in pounds per minute. This is a steady state operating curve that I was given for this. You notice it's unreliable, the operation below 50%, so we're studying it from 50 to 100. Well, the red lines here I've got marked as the different set points that I used for the analysis later on, 8, 9, 10, and 11 pounds per minute. This is just showing how the flow relay analysis is done. You've got your delta M here that you measure as you're changing the input. The delta C here is the change in the output. T is the period. So these were all measured. And in order to calculate the FU, it's just 1 over the period. The units are hertz. The KCU is 4 times delta M over pi times the delta C, and those units are percent per pounds per minute. This was one of the set points, just the graphical results that came out of it for a 9. This was one of the better results that I took. Just as an example for the 11, as it got a little bit further away from the center area, the input started to kind of jump a little bit more, and that actually led to a little bit of a greater uncertainty. And here's the results. As you can see, though, the KCU, even for all these, is virtually the same, considering the uncertainty. And the uncertainty values are a little bit smaller between here, and they got a little larger as I went towards the upper and lower ranges. But as long as it seems to be that as long as you choose something within reason, somewhere near the center, that it doesn't have much of an effect. As far as the FU goes, it was the same for all the ones that I did. So I averaged the values up. The FU is 0.3 hertz. KCU average 10 plus or minus 1% pounds per minute. Now with the proportional analysis, starting out, this was just the test that I ran. I chose the set point as being 9, and that gave me a 73% input. So this was the test that I ran to determine if that was correct and what I was going to use for the later experiments. This is just an example of one that I did with the gain being 5, and the system's really noisy. It took about 5 seconds, 6 seconds for it to reach this initial set point, and then we had some oscillatory motion in it. These are the results here that I got from the different experiments. And what I did, I took half of the KCU, a quarter of the KCU, and the KCU was actually 10, so 1/10 and 1/20. And what I noticed here was essentially the decay ratio slightly got higher as the gain went down, and the settling time was the opposite. This is the proportional integral analysis that I did, and this is just an example of one of the ones I took the KCU and divided by 2.2, got 4.5. So I used it for 3 different types of eye, and this was one of the graphs. When I went and did 4 times the types of eye, it started jumping all over the place. I mean, it was going from 0 to 100 nearly, and it took 40 seconds for it to actually then it settled out. And this is going from the set point of 9 and then stepping up to 11 pounds per minute. Another one that kind of stuck out for the different experiments that I ran was when I took a real low KC, and actually took a long time. It was monotonic, and it took a long time for it to actually get up and reach the settling point. And here's the results that I got, and what I did was I did the KCU divided by 2.2, and I changed the Taos of I. I took this one, and this is times 4, and this is divided by 4 of this value, and I didn't notice much difference in the decay ratio as far as this goes, and I didn't really see much of a pattern either in the settling times. You can note that the one that was monotonic, it took 70 seconds compared to the one that just took 4 seconds at 4.5 and 0.63. I ran the reset windup, and I did this one, and I had the set point change at 10 seconds, and it jumped around, and it ended up finally settling out after about 40 seconds. But when I ran it again and changed it at 50 seconds, it actually went almost right in line, jumped right up there in no time. So that was a significant difference. Now, I was talking about the disturbances earlier and the different wash stations turning on and off. So this is from one that I ran, and I actually had the this is with just one station running, and then I had the other station kick on, and this is actually the proportional analysis that I did. And when that happened, the extra it couldn't meet with the flow. It couldn't get up and reach the point here. And then this is again then where it shuts off, and it gets back up to the set point, and then again here where it cut back on. Now, when I did the proportional integral with the same thing, these are the points where the disturbances occurred. And as you can see, the difference here is that it was able to just quickly recover and stay at the set point. This is just showing the change in the steady state operating curve. The one that I showed you earlier here is the yellow one that I used. When it's disturbed, this is the effect that it actually has on the steady state operating curve when that other station is running. So in conclusions, I just noticed that the decay ratio increased as the gain decreased for proportional analysis, but during the proportional integral analysis with the different values that I used, there seemed to be not much difference in the decay ratio. And the proportional integral controller is it's much more capable of handling a system that has disturbances with valves being turned on and off. So, is there any questions?